Hello and welcome into lesson 11, the content video for Precalculus 1. In this video, we're going to be looking at a few different things. We're going to be looking at transformation of functions, so specifically the graphing. And in that, we'll be talking about shifting, reflecting. We'll discuss shrinking and stretching, but that'll be more used in Math 127, Precalculus 2. We will then look at algebra of function, so addition, subtraction, multiplication, and division. And then finally, composite functions. So as the name implies, one function is composed of another. So let me share my document camera for you guys. All right, so as I said, first we're going to look at our transformations, and the main ones we are going to look at is shifting. And this is vertical and horizontal. And then we will look at reflecting. So reflecting on the x-axis, reflecting on the y-axis. And then, as I said, we'll talk a little bit about stretching, but the graphs we use, they don't get stretched a whole lot. So it's just more like multiplying. So if we have like a parabola and we multiply it by 2, it just means that it's growing twice as fast. So first, for vertical shifting. So what we have is assume that we have some constant c that is greater than 0. Then we have the graph of f of x plus c. So we move the graph of f of x up c units. And I'll simplify this for us here in a second, but let me give you the official definitions here, verbiage. In the graph of f of x minus c, then we move whatever our function is, and this is the parent functions we talked about, so parabola, square root, x to the third, absolute value. So this moves f of x down c units. So the key here is just to note that if the number is outside the function, it's vertical shift, and as is, as we see it. So just as a quick example, if I have f of x is equal to x squared plus 2, well, the 2 is not included with the squared portion here, with the parabola part. So we know that this is a parabola, and because it's outside of it, it's vertical shift, and it's as we see. So I see a plus 2 meaning up 2 units. So it takes my normal parabola and just slides it up the graph 2 units. So rather than having to plot points and then draw it, we just know that, oh, x squared, that's a parabola. Plus 2, it's on the outside vertical shift. So I have to go up 2 units. Conversely, horizontal shifting, again, we'll assume C is positive. But now the graph of f of x plus c, then we move f of x, and now let's see what's going to happen here. So the function, the value now, so up above here with our vertical shifting, it was outside the function. Now my value of c is inside the function. And so I'm going to move f of x, it's a plus here, left c units. And similarly, the graph of f of x minus c, I move f of x right c units. And so again, that can be a bit messy, confusing, and so forth. So here's the way to remember it. You guys, I'm sure, have heard of the pancake place, IHOP. Well, in this situation, IHOP does not mean International House of Pancakes. What it means is inside means horizontal shifting, and it's the opposite, OP, of what we see. So for example, if I have f of x is equal to, let's do the 2 again, x plus 2 squared. So my parent function is still the parabola, x squared, but this 2, because it's inside with the squared portion, inside means horizontal shift, and it's the opposite. I see plus 2, meaning I have to go left 2. So instead of moving it up on the graph, my parabola is now going to move to the left 2 units. And again, I don't have to plot points. I don't have to do any calculations. I just know that, oh, okay, if I have a plus 2 inside, that's going to be left 2 units. Reflecting. So if I have y is equal to negative f of x, then I reflect on the x-axis. So think of it like there's a mirror there at the x-axis. It's going to flip or reflect everything down. Versus if I have f of minus x, then I reflect on the y-axis. And so again, if we want to like simplify this, my x-axis, this is if I have a negative in front. My y-axis is if I have a negative inside. So if, for example, again, I have f of x is equal to negative x squared. Well, my parent function is x squared. That's a parabola. But because the minus sign is in front, I reflect on the x-axis. So my normal parabola would look like that, right? This dotted line, that's x squared. But because it gets reflected on the x-axis, take everything downward instead. So we get this picture for the graph of negative x squared. And again, I don't have to do any plotting of points, building of tables, none of that. And then again, as far as like the vertical or horizontal stretching goes, I'll just make mention of it because again, it'll be more important if you guys go on to Precalculus 2 and you're stretching like sine and cosine curves or shrinking sine and cosine curves. Um, but it's sort of intuitive for what we have, right? Like if I have, let's say f of x is equal to 10x squared. Well, this is the parabola, but every number is growing by 10 times, right? So a normal parabola might look like this, but when I put a 10 in front of it, it's going to do what? It's going to make it tall and skinny because instead of my point being 1, 1, the point is now 110. Instead of the point being 2, 4, the point is 240, so way up top. So that's all that does. And then one last thing in terms of this section, which um, it's not really about transformations so much, but it is an important topic. And again, especially for Precalculus 2, is our idea of what we call even or odd functions. And it just says the following. The function f is even if f of minus x is equal to f of x. So if I was to take a negative x and plug it into the function and then simplify, I get the original function back. F of x is odd if f of minus x is equal to minus f of x. So what does that mean? So again, i.e., for example, if I have f of x is equal to x squared, if I plug in a bunch of negative values for x, whatever those were, -1, -2, it's going to give me the main value back. And so to check this, what we do is figure out, okay, what's f of minus x? So if you remember back when we started talking about functions, if I plug negative x into here, f of negative x is minus x squared. Negative times negative is positive, x squared, which is what I started. Therefore, x squared is an even function. And another way we can shortcut this, look at the exponents. If all the exponents are even numbers, we know it's an even function. If all of the exponents are odd, so let's say we have f of x is equal to x to the third. Well, if I try to calculate f of minus x, that's negative x to the third power, which is minus x to the third, which is negative the original function that I started with. Therefore, this is odd. And again, if I have a bunch of terms and they're all odd exponents, I know that that function then would be an odd function. All right. Not lastly, but next, let's talk about our algebra of functions. So we have the following. Let f and g be functions with domains A and B. So the domain of f is A. The domain of g is B, whatever that set B is. So maybe it's x is greater than 0, or x is every value other than -2, or whatever it might be. When we have that, if I have f plus g of x, and that's how we would say this out loud, f plus g of x, This is the same, and this is that quote, essence of math is to make complicated things simple, not simple things complicated. It just means add the two functions together. And the domain for this combined function is just the intersection of A and B. So like we were doing before, we were finding domains, taking the intersection. That's what we're doing here when we have this algebra of functions. If I have f minus g of x, this is just f of x minus g of x. And again, the domain is A intersect B. If I have f times g of x, this is just f of x times g of x. And again, same domain, A intersect B. And lastly, f divided by g of x is just f of x divided by g of x. But now the domain is a little trickier. So the domain is A intersect B such that g of x is not 0. So obviously I have g in the denominator. I can't have 0 in the denominator. So if there's an x, if there's a value that would make the denominator 0, I can't include that in the domain of this function. All right. And then lastly, we have what are called composite functions. And at the start of this video, I mentioned these. And as the name implies, composite, composed, one function is composed by another. So we're actually taking the function. We're not taking like a number at this point. We're taking a function and putting it into another function. So the formal definition is that given two functions, f and g, the composite function and we call this f of g. It has this little notation, f with the little o, I guess, for of. G is defined by, and so what f of g means is that f of g of x is equal to f, just as the name implies, or you sound it out, f of g of x. So instead of figuring out f of 2 and plugging 2 in everywhere, whatever the function g is, I plug that into the function f and then simplify. Okay, now the tricky thing with these is the domain. So the domain for a composite function it's the domain of this guy, f of g of x, intersected with the domain of g of x, which I'm going to sort of caution you here. So it's the domain of g of x in this case, because we have f of g of x. So the g of x is inside. So whatever function is inside, that's the domain that you're taking the intersection of. And the reason I point that out is I could also have g of f of x. right? And which means take the function g and plug in the f function. So now when I figure out the domain, it's going to be the domain of this new function that I just figured out, g of f of x, intersected with the domain of f of x, because that's what was inside. So that's our composite function. The idea behind what it is not too bad. You're taking one function, plugging it into another. The tricky thing comes with the domain, because we're always going to have to do an intersection with the domain. So if you're given a problem on the mastery sets or the in-class assignments, or especially on an exam, and it says, what's the domain of this composite function? If you're not doing an intersection, then you're missing out half the problem. So come on back. We'll look at a bunch of examples for all these different types of problems, and we'll see you in the example video.